this week in lab, you will be having your experiment 14 data discussion with your groups or with your class or however your lab prof is handling it. In a minute here, we're going to go through examples of the tables that you need to prepare for. We'll be checking out of your lab drawer. Make sure you bring your key. If you've lost your key, bring $10 because that's what you owe for your key. So either bring your key or bring $10. There'll be cleanup jobs you guys are going to complete, evaluations to complete, and then also your experiment 14 report is due, so make sure you get all that information when, how, day it's due from your lab prof. Then next week, a week from tomorrow, is the final exam in here. So Tuesday, December 12th, the final exam for all Chem 255 lab sections from 3 to 5 p.m. in here, okay? And I'm going to talk about that here in a little bit, but make sure that is on your calendar, okay? Okay, so let's start going through examples of the tables, and then I'll have a couple other things to add about experiment 14 before we talk about the exam. So I've got an example data sheet, so if you want to see this is the chromatogram for our example. It's conditions A that we're using, okay? So here, this may not work so well. Maybe we'll try the other guy. Maybe it doesn't squeal. Here is the data for a data set that was run under conditions A from last week, okay, or example of what conditions A would have been. So that would have been using 1 bromopropane at 0 degrees, all right? And so I'm going to go through what you need to put together for all of your tables, an example for each of those, okay? And we'll use this data for the example. So the first table that you're putting together, Table 1, is the only table that is just your data. So you will not have the data of 4 other people or 3 other people for your Table 1. It is just your data. And in this table, what you are doing is you are just listing the information, so then you have everything listed to be able to then make the calculations, okay? So you want to have a column where you list what compounds you're evaluating, so toluene, then the isopropyl toluenes, the propyl toluenes, give the standard retention times. Now these, don't use these as yours, use the standard retention times you were given. These are from a couple of years ago, okay, so they may not be valid for your data. Then you're going to give the experimental retention time and then what that percent area was experimentally. For dialkylated toluenes, so the dis and the tris are really easy to figure out because they're either, the dis are about double the retention times of the monoalkylated and the tris about triple the retention times. So dialkylated are in the 13 to 16 minute range. The tris are in the 20 to 22 minute range, okay? Anything beyond the trialkylated that you have listed but you can't identify as something, you're going to list as an unknown peak. Yes?
Retention time is 18.
Is what? 18. It could go either way. Probably more likely di than tri. A high-end di, probably. So table 1, again, is all just your data, okay? Now then, table 2, now you're going to start looking at the entire group's data. And so what you have to do with table 2 is look at only things that have to do with either toluene, isopropyl toluenes, propyl toluenes, dialkyl toluenes, or trialkyl toluenes. And for table 2, 3, and 4, you'll have a similar setup. So you're going to list what compounds you're looking at, what is the percent for experiment A, for experiment B conditions, C conditions, D conditions. So these are the A, B, C, and D conditions, all right? So where these numbers come from is now you've got to look at not just the percent of the total, but actually we're going to start looking at the peak area, okay? And so we want to, for this table, we want to look at basically everything for this set of data. We want to look at everything but the unknown, which was the peak at 26.326 minutes, okay? So what you need to do then is take all these peak areas, add them up, okay? That is your new total peak area, all right? Then you're going to take each piece that you're going to look at and divide its peak area by that new total peak area, okay? So just toluene is going to have this peak area divided by this whole peak area added together, okay? Then the isopropyl toluenes, these 3 will add together and divide by the whole total area. The propyl toluenes will add these 3 together, divide by the whole total area. And then you'll get to your dialkylated, add their areas together, divided by the whole total. And the trialkylated, their areas together, divided by the whole total. Does everybody see that? Okay. So in the end, if you have done this correctly, each of your columns should add up to 100%. All right, so that's kind of the check on the math, is that each of these columns should add up to 100%. All right. So then the next table, you're just going to look at the isopropyl toluene. So now you've got a much smaller subset that you're looking at. So it's just these 3. You'll add those 3 areas together. That's your new total area. And then you'll divide each of these individual areas by that new total area to come up with the percentages for meta isopropyl toluene, para isopropyl toluene, ortho isopropyl toluene, right? And again, it should add up to 100%. Yes?
Are you supposed to keep the unknown out of the total?
Yes. So like on table number 2, that's why you had to recalculate that area, because you had to get rid of the unknown peak, or however many unknown peaks you have. Okay, so again, should add up to 100%. And then for table 4, this is what our table 4 should look like for the propyl toluenes. Okay, so again, you're looking at just the propyl toluenes, add those areas together, and then divide each individual area by that new total to come up with the percentages. Now, ideally, for the propyl toluenes, you're only going to have data for A and B. However, if you do have information for C and D, don't necessarily discount it, although it's probably going to be a really, really small amount, okay? So if you fill in the table, it's probably going to look really large because it'll be one entry that'll be 100%, but in the overall scheme of things, it's going to be, you know, like a 0.2% area or something like that that you're adding into, okay? So kind of be careful if you end up putting something in column C and column D to make sure that you know and the members of your group know that in the end that started as a really, really small number relative to anything else. And it is possible that you get some of the propyls in C and D, but probably just a tiny little amount, okay? Especially D, maybe not so much C, but especially when you heat them, there's a chance that you could get propyl toluene in D, right? So when you come to lab this week, you want to have your tables prepared, and there's multiple ways that these are being prepared. Either some profs have Google's worksheets that you're filling out, Google Sheets you're filling out. Some people are having you come with them prepared, but just make sure that whatever you are supposed to do before you come to lab this week, you take care of that. Because then in lab, you want to be able to discuss this data. And so on page 14-8 of your lab manual, there's a series, after it gives you the instructions for all the tables, there's a series of questions that you need to use to help you analyze the data, and that's what you want to be able to discuss within your groups, all right? And then those discussion points, you want to make sure you add into your conclusion, but you don't want to just label them, 3, 4, 5, like you're giving answers. You're going to incorporate it into the final conclusion that you're writing for experiment 14, okay? But in order to get all the data discussed and all the points covered that you need to address each of those points, right? So it might be a good idea beforehand to be familiar with what you're going to need to look at with the data, all right? Questions at all with the data? Okay. All right, so pull this down for just a second here. Other things to think about for experiment 14 are your analysis is basically based on GC information, but don't forget that you also need to figure out your yield, okay? So remember that you want to use your own GC data to figure out what percentage of your GC data was product and multiply that times the yield that you calculated last week. Because remember, you measured just what the total mass was of the mixture at the end of working it up and drying it. Now you've got to figure out how much of that is product, figure out what part of it is product, and then go back and calculate a percent yield from that, okay? So you have to use GC information to figure out what percentage of the grams is product, and then calculate percent yield. Does everyone follow that? So there's two steps to it. You have to use your GC data first, then go through and calculate the percent yield. So that's something that you'll also need for your conclusion. Now, when you are going through the questions, a couple things to think about. We talked about last week the different products that could have been formed with Frito Crafts, and ortho and para versus meta, and what's kinetic and what's thermodynamic. And then we also talked about the carbocation rearrangement. If, when you're writing things up and putting things together for your conclusion, if it's getting confusing, who's kinetic versus thermodynamic, use the kinetic versus thermodynamic discussion for the products and talking about what the different products are under different conditions, and talk about the rearrangement as the rearrangement. So if you're addressing what is happening in the rearrangement due to heat or due to whatever initial alkyl bromide was used, talk about the carbocation rearrangement versus trying to address what's kinetic versus thermodynamic. Think about what the products of the reaction were, and you have to look at what those products were. Okay? All right, so that's pretty much all I had for 14. So now I'm going to give you a little bit for the exam real quick, and then we'll talk about the practice exam. So on Tuesday, things to bring to the exam. First of all, you are able to use calculators, okay? Bring your own calculator, okay? The memory should be erased, so it shouldn't be full of all sorts of really nice organic lab information. And you can't use a cell phone as a calculator. So you have to have an actual calculator. So make sure that you have a calculator with you. Bring a calculator. You may also bring a ruler. So when would you need the ruler? For information for TLC, right? Okay, so you are able to bring a ruler with you. So good idea to bring that along with you as well. Please bring pencils and erasers versus trying to take the exam in pen, okay? You want to make sure that your answers are very clear, so make sure pencils and erasers versus trying to do it in pen and then scribble out what you want and what you don't want, okay? So that it is very clear to us when we're trying to grade it, all right? The format will be similar to what you had with the practice exam, okay? So multiple choice questions. Things to think about are, things covered in lab lecture, things in your lab manual about the the theory behind reactions or why you did things in reactions. What we won't ask you is like the nitty-gritty detail of a specific experimental. So, did you use 5 grams of a reagent or 6 grams of a reagent or 7 grams of a reagent? We're not going to ask you that kind of information. But I would know why you used that reagent. I would know, if you use that reagent in excess, why did you use it in excess? Or if that was the limiting reagent, why was it the limiting reagent? So things like that are important to know, but we're not going to ask you, in the Grignard reaction, how many milliliters of ether did you use to extract the aqueous layer? That's not going to be one of the questions. Yes?
Will there be questions about historical figures and dates?
Probably not. It won't be a focus of a history exam, no. So think of the context of, the bulk of what was covered for lab lecture, what you did in labs, things like that, all right? And it is tied to lecture, so if there's information in lecture that can help you, by all means, as you're trying to figure things out, like don't just block out what you've learned in lecture, okay? Like they can go hand in hand and help you to figure things out, okay? All right, so we'll go quickly through the exam. If anyone needs a copy of the exam, it is on Moodle. There are actual paper copies in the back too, if someone needed to grab them, paper copies. First note for the exam. Don't forget that there's a point for your exam on the first page, okay? Don't forget that easy first point. It will be marked off if it's not marked, all right? So, easy point. All right, so let's start going through the exam, guys. Starting with number 1. So we're looking at a good recrystallization solvent and what characteristics that would have. So a good recrystallization solvent is one in which the compound to be purified is very soluble at all temperatures, insoluble at all temperatures, quite soluble when hot, fairly insoluble when cold, or fairly insoluble when hot, quite soluble when cold. Which one is it? C. So we want it quite soluble when hot and fairly insoluble when cold. During typical recrystallization process. Solid impurities are more stable than the desired compound. They separate because the impurity dissolves in the hot solvent mixture and remains dissolved, never dissolves in the solvent and is gravity filtered, dissolves in the hot solvent mixture, but then precipitates upon cooling, does not dissolve in the hot solvent mixture, but then dissolves as the solvent is cooled. Which one is that one? A. So you want the impurities to dissolve in the hot solvent and stay in there. All right. A benzoic acid and a neutral compound are dissolved in an NaOH hexane mixture and the layers are separated. What is the best way to recover the benzoic acid? Neutralize the basic extract with HCl and then collect the resulting precipitate. Dry the ether solution with magnesium sulfate. Simply filter out the solid on a Buchner funnel and dry. Distill the water off of the benzoic acid. A, right? Just like the very first experiment, okay? All right, which are in identical conformations? So we've got 1 and 2, 3 and 4, 1 and 3, 2 and 4. D, 2 and 4. Okay, so this Fisher versus this Sawhorse. Okay. All right. Which compound is the least polar? Soluble in water and soluble in diethyl ether, soluble in ether and in concentrated sulfuric acid, soluble in water, soluble in diethyl ether. So the least D, right? So if it's only soluble in ether, it's not going to be that polar. And sorry, wrong, Newman projection, not Fisher. Calling things the wrong thing. All right, number 6, I can't really quite show you all the answers because we got to go through the calculations, okay? So we've got our compound 1 reacting with, so we've got our triester reacting with our sodium hydroxide. We're going to make glycerol and then the sodium salt of our acid, all right? And we've got to figure out what is the limiting reagent, okay? So we'll go through, we'll take 3 grams of 1 divided by 723, okay? So here's our trimeristin. We'll go through and calculate how much NaOH we're using. Now keep in mind, what is the ratio of trimeristin to NaOH that you need to use? 1 of these to 3 of these, right? Okay. And then we'll calculate how much ethanol, all right? So 3 grams divided by 723 is 0.00415 mole. If we go through, so I started with this being, instead of 5 mils, 0.005 liters times 2 moles per liter. But then we also have, sorry, it's a little bit, it looks like it's supposed to be a liter. It looks like a 3 here. 2 moles per liter, and then we multiply it by 3. We need 3 of these for every 1 mole of our trimeristin, okay? So we get 0.03 moles here. The ethanol, when we go through and use volume and density, and then molar mass, we get 0.17 moles. So our limiting reagent was B, number 2, okay? So in this case, we're asking you to make a calculation for a reaction, but we're giving you all the information that you need for making that calculation. Okay? Infrared spectroscopy. Identify compounds based on boiling point. Separate compounds based on polarity. Identify functional groups in a compound based on vibrational energy, or calculate PDI. C. The extraction yield in a solid liquid extraction could be increased by all of the following techniques except choosing a solvent that the solute is more soluble in. Is that correct?
For number 6, we got 0.004.15 moles.
Oh, sorry.
And 0.03 moles of cyclone, so why would...
I think I'm off a decimal here. Yeah, I was off a decimal.
Should 0.0005.
No.
Yeah. No, it should be 0.005. But then, so somehow I messed up my math. The answer should be B.
0.0033.
Yeah, I'm off on my decimal points here. So the answer should be B. I'll double check my math here, because I made a mess by writing like things that shouldn't be there. So when I post, so I will post this on Moodle as well. I'll double check this guy before I post it, but I'm going to post it, like I'm not going to post it today. I'll post it like later in the week, so everybody has time to look over the exam before I post the answers, okay? All right, so back to number 8, choosing a solvent that the solute is more soluble in, that would be a good thing, right, for the extraction. So that's not an answer. Performing a longer distillation, would that help with your extraction? No. So the answer is B. Increasing solvent volume would help, and repeating the extraction process would help. Okay. All right. A student desired to make M-isopropyltoluene from Friedel-Crafts reaction with toluene, but only had 1 bromopropane. To maximize the yield of this product, what should the student do? So keep the reaction mixture at -20, heat the reaction mixture at reflux, keep the mixture at 0 degrees, not run the reaction because the product won't form. So it's B, right? If we heat it, we'll get to that, guys. Okay, out of the following choices, what is the best method to separate liquid compound A from liquid compound B if liquid has a boiling point of 25 and liquid B has a boiling point of 125? Separation, solid liquid extraction, reflux, or simple distillation? Simple distillation. Erlenmeyer's unknown carboxylic acid melted at 118 to 122 degrees C. The mixed melting point with a reference benzoic acid sample was 122 to 123. And benzoic acid melts from 122 to 123. He retested using a different thermometer and his values were the same. He concluded that his unknown was not benzoic acid. His unknown was benzoic acid but was impure. Both thermometers were misbehaving. The reference benzoic acid was impure. It was a bad day in the lab. B, right? Because he's got this melting point. But then the mixed melting point is here in line with what the melting point should be. So he's initially starting with something that's a little bit impure. So it's B. Okay, a positive result is obtained when performing ceramic ammonium nitrate tests, which IR spectrum matches the result. So ceramic ammonium nitrate, what are you testing for with ceramic ammonium nitrate? Alcohol. So with experiment 6, it would be good to know with the chemical test, what are you testing for, okay? And know basically what those functional groups look like by IR. It'd also be good, we're gonna get to one here in a little bit when it gives you some information. Well, we kind of already did a solubility one. There's gonna be another one here in a little bit that gives you solubility information from experiment 6. So it'd be a good idea to have a familiarity with that as well, okay? So which IR shows an alcohol? D. So this one is probably, I think is like alkene. This guy's carbonyl. This guy's potentially maybe alkene as well, okay? But this definitely has the broad OH stretch for D, okay? Which of the following does not describe a Diels-Alder reaction? Pericyclic, concerted, stepwise, 4+2 addition, cycloaddition. Stepwise.
What is concerted?
It happens all in one step. Okay. So here's another conformational one. Which are conformational isomers? 1 and 4, 2 and 3, 1 and 3, 1 and 2. Thoughts on that one? A, right? 1 and 4. Okay, 1 and 4. You kind of almost get tripped up with 2, but you've got to look at equatorial versus axial. Okay, so these are both equatorial versus axial, and then axial, but also the cis-trans relationship too. Okay, the up-down relationship. When one equivalent of tetraline, so here's tetraline, is reacted with one equivalent of MBS, they go through radical bromination. What is the product that is formed? So of these choices, what product is formed? It's B, right? Because you brominate the benzylic position, okay? So none of the rest of these are showing a bromination at the benzylic position. Okay, here's our, kind of a yield calculation. Following a Grignard reaction, you obtain 5.3 grams of product, and you had a theoretical yield of 7.0. The GC shows that it's 83% product, 14% ketone, 3% unreacted starting material. Which of the following is the best approximation of your actual reaction yield? Okay, so first part, we've got to figure out what the 5.3 divided by 7 is. Okay, so that's about 76%. Then we have to multiply that times the fact that it was 83% product from the GC, okay? So then we get to, 0.628, which is about 0.63, which is 63%, so it's C, okay? So this is similar for what you're going to need to do. In a similar way, you're going to need to use your GC data for 14, except for you got to start with the GC data and then calculate the percent yield. Okay, so you'll do it in the opposite order. Okay. We've got polymerization of styrene to form polystyrene, and it's initiated by AIBN. Okay, so here's our AIBN. This is what's formed. We get 2 AIBN radicals and we give off nitrogen gas, right? Then one of those AIBN radicals reacts with styrene and we go on and form the polymer. We've got to figure out N for this given polymer, okay? So we have 3.5 grams of styrene that's reacted and 0.01 gram of AIBN. We need to figure out how many monomer units we have, okay? So what you start with, didn't print very well, sorry. So 3.5 grams, we're going to figure out how many moles of styrene we started with, okay? So that was 0.0, it didn't come out very well. This is 0.0337 mole, okay? Same with the AIBN, we started with 0.01 grams divided by 184, but remember, for every AIBN you get 2 radicals, so you'll get two reactions with a polymer versus 1 mole of AIBN, all right? So if you multiply that out, you get 0.000109 mole AIBN radical, okay? Because for every AIBN, you got 2 radicals out. So then, what you need to use is the mole ratio of the 2, okay? So if we take the styrene divided by the AIBN, knowing that each polystyrene starts with 1 AIBN radical, then we get to that there's 310 that could form. So your N is 310. So it's a little bit different than what you did for your own experiment when you were calculating N, knowing how much your polystyrene weighed. You could have also done things this way to figure things out for your sample. Okay? So the answer is F. Okay? So in the end, calculate the moles. Keep in mind you're talking about AIBN radical, find the mole ratio, and that's how you get to that answer. Okay? All right, this one is just asking which of these is the structure of benzoyl peroxide. So which one is benzoyl peroxide? Do you remember which one it is? B.
Wait, B or E?
B. So you had, remember benzoyl peroxide, we had the breaking of this. This was the reactive bond that broke to get your radical initiator. Okay? So you do have to remember some of the chemistry that you did. Okay? All right, identify the following reactions, which is not, among the following reactions, which one is not a propagation reaction? So A, we're using Br radical to form a benzylic radical. B, we're reacting NBS with HBr to get Br2. And C, we're taking our benzylic radical, reacting it with Br2 to brominate our ethylbenzene. So which one is not a propagation step? B, right? It also doesn't involve a radical, so that would be kind of a clue that it's not part of the radical chain reaction, right? It's not the propagation step there. Okay. The following dry bromide is subjected to quinoline-induced double dehydrobromination. How many isomers of dialkenes can it produce? Thoughts on that one? It's not one. I'll give you that hint. So if you think about cis and trans isomers, because right, you're going to be making double bonds here. It's 3. It's C. So I'll let you guys play with that one figure that one out on your own time, but it's related to cis and trans isomers, and the answer is C. Upon addition of magnesium sulfate to your ether solution and waiting for 5 minutes, you notice several clumps of solid along with free-floating particles. What statement best summarizes the situation? There was some water present, but your solution is now dry. More magnesium sulfate must be added to completely dry the solution. The clumps must be removed before you can continue drying the solution. There was never any water in your solution to begin with. A. So you're always looking with magnesium sulfate for clumps with a low free floating. That means there was water present, but now it is getting dry. Okay. A student received a gel permeation chromatogram for their experiment 7 polystyrene product with the following values recorded. Mn was 4845, Mw was 10593. What was the PDI for this sample? So how do you calculate PDI? Mw divided by Mn, right? So you get 219, so the answer is D. Okay. The product below can be prepared by which of the following? So here's our product. Which of the following reactions? Assume a weak acid workup. A, B, C, D. Which of those looks good for forming a tertiary alcohol? A, right? Because you're starting with a ketone for the Grignard reaction, so you'll get to the tertiary alcohol. Okay? If terbutylbenzene was used instead of toluene in the reaction of 2-bromopropane and aluminum chloride under kinetic control, which of the following products would decrease in percentage of the total products? So terbutylbenzene and 2-bromopropane, it's under kinetic control. So what does that mean as far as products you'll form? ortho and para, but you're going to decrease the percentage of one of those, so which one would you decrease? Ortho, because of sterics, right? Okay, following the Grignard reaction below, you attain a GC with peaks 2.54, 5.87, 9.31. Which is the correct assignment of these peaks in order of increasing retention time? So we've got A, the alkyl bromide, B is our aldehyde, C is our product. So just based on GC information from experiment 8, where did the product fall as far as retention times? Because those were pretty high boiling, right? So those were in the 7 to 9 minute range. So product is probably over here, right? Is an alkyl bromide or an aldehyde going to boil at a lower temperature? Alkyl bromide is going to boil at a higher temperature than the aldehyde, okay? So then at 2.54 minutes is B, 5.87 minutes is A, and 9.31 minutes is C. So the answer is B. Okay, what is the theoretical yield of alcohol in the reaction below? Okay. So here's our reaction. We're doing a Grignard again, okay? So what I did is I went through and I calculated how many moles of each of these were used. So I got 0.0315 for compound 1, 0.082 for compound 2, 0.034 for, 0.082 for the magnesium, 0.034 for 2. So the limiting reagent was 1. So when you use that multiplied by the molar mass of the desired compound, you get 4.29 grams as theoretical yield, so the answer was B. Okay. Give the 3 mechanistic steps for the Friedel-Crafts alkylation of toluene in order of occurrence. So what do you start with for the Friedel-Crafts alkylation? What has to happen first? What piece happens first? It should be like fresh, covered it freshly in lecture and lab. So forming the carbocation, right? That's number 1. So then what does the carbocation have to do? React with the aromatic ring, right? So 1, 2, and then what's the last piece? 3. We've got to lose our proton, okay? And the difference between 3 and 4 is thinking about where would that carbocation be? Where would that charge be on the aromatic ring? Okay. So the answer is 2, 1, and 3. Answer B. Okay, which of the following compounds represents the Cyclopentadiene Dimer? C is right. Now, if you didn't know that, if you knew that cyclopentadiene, it takes 2 cyclopentadienes to make 1 dicyclopentadiene, what would you do to figure out what the answer is? Do the Diels-Alder reaction, right? Because you break apart dicyclopentadiene with the retro Diels-Alder. So 2 cyclopentadienes will do a Diels-Alder to form the dicyclopentadiene, okay? So the answer there is C. So this is not just purely memorization, all right? Okay, which of the following pairs of compounds would be most reactive in a Diels-Alder reaction? So what do you want for your diene? You want what conformation? S-cis, okay? So A, B, or C would be a good possibility, right? What do you want on your dienophile? Electron withdrawing groups, right? And the more electron withdrawing, the better. So of these possibilities, what would have the best electron withdrawing groups? C, right? C or D, but the problem with D is this is not in the S-cis, right? Okay, so C is the answer. Okay, which of the following alkyl halides would give the fewest number of potential products in the Friedel-Crafts reaction with toluene in the presence of aluminum chloride? Fewest number. So what would kind of be the key there? What's not going to happen most likely? Carbocation rearrangement. So you want to look for one where you're not going to get that to happen. Will that happen with A, B, C, D? No. So the answer is D. IR spectrum for an unknown compound has a peak of 30, 50 inverse centimeters, characteristic of an sp2 stretch of an alkene. To confirm the presence of an alkene in the unknown, what chemical test should be performed? So what's at 30, 50? An sp2 alkene. What was a good chemical test for that one? Alkenes. Potassium permanganate, right? What's another good one for alkenes? The bromine addition, okay? So just remember that one as well. Okay, here are the last two. Okay, we've got this TLC plate with a whole lot of stuff going on, okay? Considering the following TLC data for a Diels-Alder reaction between A and B, so you're reacting A and B to make C. The TLC lanes are labeled as shown below, so we've got 1 through 5. We've got starting material A, starting material B, reaction at 5 minutes, reaction at 30 minutes, reaction product after recrystallization. Which of the following is not true? So starting material A is most nonpolar component of the reaction. So lane 1 was starting material A. Is that true? It is the most nonpolar, right? Because it has the highest RF value. At time 5 minutes, a product had formed. So at our 5 minutes, which is 3, we've got our A, our B, so A and B, and then we have a new spot. So something had formed at 5 minutes, all right? The product at 30 minutes shows impurities. So at 4, that's the product reaction mixture at 30 minutes. Do we have any impurities in here? We just have one spot, right? So that is the answer, is D. But let's look at E. The product decomposed into starting materials during recrystallization. So we've got, here's our recrystallization. We no longer have our product spot anymore. It had decomposed back to its starting materials, okay? Another note about about TLC, how did you visualize the TLC plates? How did you visualize the TLC plates in lab? UV lamp, right? So what did you need compounds to be able to see them under a UV lamp? They needed to be UV active, right? What kind of compounds are really good UV active compounds? Highly conjugated, okay? So in the case of experiment 12, what was your highly conjugated part? What was on your product and on your starting material? Aromatic rings, right? So just keep that in mind when you're thinking about what would be UV active. Usually most aromatic rings are going to be UV active. in addition to things that are very highly conjugated throughout, okay? All right, which of the following is not a correct mechanistic step in the dehydration of an alcohol with sulfuric acid? So A, we react with the acid, the alcohol reacts with the acid to form water. B, we've got water leaving, and we also have the deprotonation occurring. C, we have water leaving, forming our carbocation. And D, then we have either water or the conjugate base of our acid deprotonating to form the alkene. So which of those is not mechanistic step? B, right? Because it doesn't happen all in one step, okay? So what type of elimination is this? It's an E1, right? Okay. Versus what happened with the dehydrohalogenation? What type of elimination was that? E2. It happened in all of that stuff. Okay. Okay. So I will see you guys a week and a day from today for the exam.